So here we find our familiar figure. We're going to be able to refer to this figure again, probably also the one on page 70 when we talk about basically, the structure, what's happening with a semi-confined aquifer. Both of these drawings here, the one on the left in black and white and the one on the right in color, kind of show the same thing. Again, just to kind of set it up that you understand what we're talking about when we are talking about this type of aquifer. And we're going to have several rules or several stipulations when we're doing this type of analysis. One is that, well, here we have our confined aquifer. I'm just going to use the one on the right-hand side. It's nice and colorful. Obviously, it's screened. Okay, so we have these arrows representing radial flow. So again, we like to have the full screen interval covering the whole confined aquifer. Below the aquifer is an aquiclude. And remember, the difference between an aquiclude and an aquitard is an aquitard may allow some flow through. Nothing that you typically are going to be able to produce and have a great well from, but an aquitard is going to be an aquiclude is going to be a no flow boundary. So let's just remind us of that. Again, the aquiclude is going to be impermeable and is a no flow boundary. And for all intents and purposes, we're just going to still kind of assume the aquifers are of a infinite lateral extent, so we're not going to get into lateral boundaries right now. So you'll notice that the aquitard above, we have these little arrows. So if I just kind of extend these arrows, and they're kind of extended on the picture to the left, what that is groundwater seeping through the unconfined aquifer above, through the aquitard, and eventually making its way into the aquifer. Okay, so I'm just going to kind of extend these arrows just a little bit. Okay. And because it's able to transmit this groundwater, this aquifer now is semi-confined. So let's just stipulate that right now. We'll call it semi-confined. Again, because we have the transmission through the aquitard, and it's also leaking, or a leaky aquitard. And above it, we have our old unconfined aquifer. Okay, so going with this, there's going to be a set of variables as well that we're going to see that we're going to introduce for a mathematical kind of leakage rate. And we're going to have to take this into account when we're looking at the overall recharge of the system. So I'm just going to insert a page. I just want to write a couple of notes here. Most confined aquifers are not totally isolated from sources of vertical recharge. Again, we'll just focus on vertical. Aquitards, either above or below, can leak water into the aquifer if the direction of the hydraulic gradient is favorable. In that context, we'll just consider the aquitards on top of the confined aquifer, and we'll look again as that picture showing as the aquiclude or bedrock below that confined aquifer. Okay. And recall that an aquitard, just for a definition of an aquitard, is a body of relatively impermeable rock. So there is some flow, some minor flow, that is capable of absorbing water slowly, but doesn't transmit it rapidly enough to supply, wells, springs, etc. That is, it has restricted flow. So there is flow, as you saw in those cartoons, but it is restricted. Okay, so let's continue on. Let's look at some equations and let's get into some math, right? Okay. So introduction to semi-confined aquifers or leaking aquifers. So I'm just going to remind you that either term is acceptable, or leaky aquifers. So I guess that's 3 different ways of thinking about it. Let's find my highlighter here. Let's go for yellow. Let's do that. Okay. So again, just repeat what we saw in the graph. A semi-confined aquifer, or leaking aquifer, is similar to a confined aquifer, right? Except the aquitard that overlies is more permeable, allowing water into the aquifer. Okay. And we're going to, again, unfortunately, have to go back to well function tables in order to satisfy our equations again. So we see our old friends, these W's and these integrals of infinite extent, etc. So we're able to quantify a leakage rate, but we have some additional variables to consider. And there's a couple of different little elements to look at here too. We see that there's a B prime. Well, typically B was going to be our height of our aquifer, but now it happens to be the thickness of our aquitard. Okay, so that, or the thickness of the confining layer. Okay, we have our K, and you know K, of course, is hydraulic conductivity. So we have to know or determine the hydraulic conductivity of the confining layer. Oop, hydraulic conductivity of, I'll just put CL for confining layer. Okay, and all that is going to be used, and we've seen our drawdown before. All that is going to be able to determine a overall leakage rate. And H minus HO is just drawdown. So not too bad. Just a couple of more variables to consider. It kind of doesn't really end there yet, because we also have to consider the properties of the aquifer above the aquitard as well, or that potential unconfined aquifer. So it's going to get yet one level of mathematical complexity above what we already have. Okay, so leakage rate of the aquitard, W, can be determined by Darcy's law, or I guess a version of Darcy's law. The vertical hydraulic conductivity of the leaking confined aquifer of the aquitard is K prime. And again, when we're talking about vertical, we're talking about vertical conductivity from above and transmitted throughout. Hydraulic gradient is the head across the layer, which is equal to the drawdown, as we know, and the thickness of the layer, and that's the confined layer, is B prime. Therefore, we can establish the leaking rate. So we're going to get back to this, but we're actually going to use it in a kind of a different form when we're doing our math associated. Question, and this is a question right from the Feder text that he poses to his students as well. Where does the water flowing to the well originate from in the case of a semi-confined aquifer? And the hint for this is it's actually the same as that for confined aquifer. Where does the water flowing to the well originate from in the case of a semi-confined aquifer? It is still elastic storage. Okay, it's still that water that is going to come out of compressibility. That's still that first water. It's drawing into the aquifer through aquifer storage, through elastic decompression. That's still the same water that's going to be originated from the semi-confined aquifer. Okay, so this Hantush method, and I'll just change it a little bit. It's actually not just called the Hantush method. It's called the Hantush-Jacob method. The same Jacob from Cooper-Jacob, you'll recall, from the confined aquifer analysis. Accounts for all water coming from elastic storage in the aquifer or leaking across that confined layer. So we'll have a new set of equations, and some new variables to contend with. So there is a very similar layer. There's our confining layer, or I'm sorry, a similar graphic as previous, and that we could also call that the aquiclude. We see that we have a fully penetrating well, and as we go out an appreciable distance from that fully penetrating well, we could use it to estimate drawdown or various other properties at some radial distance from the center of the well. Remember, R is always measured from the center of the well. Okay, so we have that radial component or that lateral geometric component as well. We have the height of our confined layer, also with its hydraulic conductivity, sortivity, and transmissivity. If you wanted to include that, we sure could do that as well. And then we find the same variables, or those same variables are going to be established as prime functions. So B prime hydraulic conductivity is K prime, S prime for storativity. And then one step further, realizing that the origin of some of this water is from the unconfined aquifer above, and it looks like we're already pumping in this situation, right? Because we already see a drawdown, i.e. a cone of depression. We're going to call that B double prime. Okay, so this is a useful table to come into to kind of visualize, conceptualize these parameters. If you are challenged, as we will be challenged with several questions, if you kind of have a hard time visualizing what's going on, maybe not only refer to this little drawing, but sketch yourself like a little picture of the geometry, so you kind of have it straight in your mind what's going on, because it's very easy kind of to mix up these functions. Okay. And then another note, I was just looking at my side little notes here. This looks like a fairly thin layer. This aquitard looks fairly thin in this picture. There's really no scale implied. It could be a very thin layer, or it could be a very thick layer. If it is a a saturated thick layer, there could actually be a fair amount of water transmitting from it, as well as from the unconfined aquifer above. So that's something to keep in mind, that this geometry isn't fixed. Obviously, this is kind of an idealized schematic for the course pack, but your leaking confining layer, especially around here, we have such fine-grained sediments, can actually be fairly significant and be a major source of that water going into that lower leaking aquifer. Okay, so don't just think of it as just kind of a little wedge or something, or a thin little bed. Obviously, it's going to change in geometry as we go through different situations. So the Hantush method's been around for a long time. So I'm just going to go ahead and put Hantush-Jacob method. And if memory serves me correctly, I think it was around 1956. Okay, so this is nothing new. We've been studying this method for about 70 years, and it's kind of tried and true, and it follows some basic assumptions. But then ask yourself, as I read these out to you one by one, like, are these a little bit overreaching? Or, how well do these reflect nature? Okay, because we've always been talking about the lateral extents and isotropic conditions, etc. Ask yourself if these are if these make sense and if they're overreaching. Let's look at the first basic assumption. The aquifer is bound on the top by an aquitard. Okay, I think we can live with that. They're not saying that the aquifer has to, the aquitard has to have a certain geometry. It just has to be bound on the top. Okay, nothing really too controversial about that. The aquitard is overlain by an unconfined aquifer known as the source bed, and that's what we have right here. we have an unconfined aquifer. And that's known as the source bed. Okay, realizing that this well is under pressure, so we have the potentiometric surface of the confined aquifer. So this would all be water. Let me just find a blue here. Just kind of give it some color here. This would all be water, right? This is going to be water all the way through and water all the way throughout. Kind of give it some life. Okay, but when we are pumping, because we have this leaking confining layer, that will be the source bed for additional water. Again, nothing too controversial with that. Again, if you look at the image, it kind of looks straightforward. The water table in the source bed is initially horizontal. So what they mean is initially horizontal prior to pumping. Again, we realize that on a large regional scale, and if we adjust that scale, it may not be purely horizontal, but we're not going to worry about gradients for right now. We'll just assume that the water table, and typically over your site, it's not going to vary by too much. So that would kind of hold true as well. Here's another one. The water table in the source bed does not fall when the semi-aquifer, confined aquifer is pumped. The water table in the source bed does not fall when the semi-aquifer is pumped. Boy, that one's a little bit tough. That almost considers like we have infinite recharge into the unconfined aquifer. That one is a little bit hard to kind of wrap your head around, right? That means that you're talking about static conditions while you're pumping. You know, you're not getting a change, drop down of water level. But again, that's a basic assumption as done in this calculation. So let's continue. Groundwater flow into the aquifer in the aquitard, is vertical, again, under gravity, and you see that, or we could actually add that in. And it was just like this in the previous pictures. The transmission through the aquitard from the unconfined aquifer is going to be vertical, just due to gravity feed. Don't really have a problem with that. The semi-confined aquifer is compressible and water drains instantaneously with a decline in hydraulic head. Again, basically that's saying that we have elastic storage, and as we get a decompression of the aquifer, the water is just kind of coming out due to elastic storage, and that's a basic principle of how water is produced from a confined or a semi-confined aquifer anyways. And as we say here, the aquitard itself is incompressible. Okay. So which of these assumptions seems least realistic? And I said number 4, actually, and I kind of gave that away, and maybe I shouldn't have, but that one seems a little bit unrealistic, that, you know, we go ahead and pump, that we're not going to see a change in water level in the unconfined aquifer. Again, unless we do have continuous recharge in the unconfined aquifer, then that would be true. But what we have to do is test your equations before you continue, or test the efficacy of the overall situation to see if it will fit within the model of the Hantush-Jacob's theorems. So unfortunately, before we kind of get going and try to calculate, the end result, we have to do again some checks to see if this is applicable. It's kind of like when we did the U check on the Theis analysis, making sure that the data as continued on is going to be valid or not. So we're going to have a couple of different checks here to check for the efficacy of the Hantush method. And we'll just kind of go through these as an example function. So we have kind of an either or situation where we could do a time function versus storativity or a hydraulic conductivity of the confined bed in relationship to the hydraulic conductivity and the thickness of the semi-confined bed. So we'll kind of get back to these, but see the graphic above. For these variables. Okay, when I say see the graphic above, it's just these guys. Okay. Actually, let me just take out this T because I don't want to confuse anybody. Okay. And it doesn't end there. We have to do one test. And we have to do two tests for assumption 7. Assumption 7 says no water is released from the aquitard under all these conditions, but we have to verify if that is true or not with a set of either or of these conditions. Okay, so basically you have to pick an equation depending on the data set that you have from the first set of equations, and then you have to, if that passes, it's kind of like a go, no go, then you're going to proceed on to the next set of equations. And again, based on the data that you have in the question, see if you're going to meet the conditions. And again, T here is going to be time, not transmissivity. That's going to be time. And then if you pass that set of conditions, then you could go on with the method and you could go on and run your analysis. Okay, so it's kind of a bit of a rigmarole to kind of get the final results. But again, that's kind of the way it is. So long story short, if these conditions are satisfied, if 1 and 2 are satisfied, the method applies, and you could go ahead and give her with your results. Now, what is the equation that you're trying to determine? Well, what you're trying to determine typically is going to be a drawdown, because a lot of times we already have a storativity provided to us, or transmissivity. It kind of depends on the nature of the question. And you see that we have a well function again. Okay, so what this means is, yes, we are going to have to go back to data tables. And we're going to have to do interpolations. And I'll draw a little sad face because it's just the way that it is. But here is the Hantush equation for non-equilibrium flow in a well in a semi-confined or again a leaky aquifer. Okay, so we have drawdown. Remember that still our pumping rate has to be constant. We have to be very cognizant of our units of measurements. That if we're in days, we're not multiplying days times minutes. We're not multiplying meters cubes by feet, that type of thing. And drawdown is still a little s. Capital T is still transmissivity, again, of that semi-confined aquifer, that lower aquifer. And then we have this well function to contend with. Okay. And we still have our U function. You're going to see how that parlays, and we'll do a sample calculation so you can see how that fits into the schema of everything. And we have another calculation for a variable called B, our leakage factor. If we go way back to the aquifer leaking function, we have this B that we haven't seen before. Okay, this capital B, we've seen the lower b before, but we haven't seen the capital B. So this is going to be something new. It's going to be the square root of transmissivity, again, T, multiplied by the aquitard thickness, divided by the hydraulic conductivity of the aquifer thickness. But in this fashion, it may not be completely useful. So what you're going to see me do when we are doing an example problem is we're going to modify this equation to take in count of a radial distance. And if I just introduce r into that, little r, which is going to be a radial distance away from the well, I can use this same equation to give me an r over b factor. Give me something like this. Okay. This will make a little bit more sense when we're using the data table, because unfortunately the data table doesn't give us the B leakage factor natively. It gives me an R over B, so I have to modify this formula ever so slightly. And remember that the conductivity that we're looking at is going to be the vertical conductivity. Right? Or the vertical K prime, because we're looking at the water migrating through the aquitard to the semi-confined aquifer below. So we don't have to worry about anisotropy if there is a difference in conductivity laterally. Okay, so again, it's vertical conductivity. It may not be specified. In fact, it won't be specified, but that is the overall arching case. So I'll work together with you guys on the sample problem, and you'll have 3 other opportunities in lab 10 to with multiple equations in each again. So I suggest that you use Excel in order to kind of wrap your head around how this all works. Okay, so before I do that, you need a data table, and this is taken exactly from Feder. And we're just going to take a look at it for a second. So remember I said, first of all, when we're using, when we're doing leakage calculations, this version of the table is an R over B plot versus U, our well function. And we're looking fairly at typically small values of U. So we're going to be looking at typically this row of U and comparing it to values of R over B. And when we see on the top right-hand quadrant, we see these lines that go from one point to the next. Basically, to make the table look a little bit less muddy, these lines just show that the values do not change all the way through. For example, at a ratio of R over B of 0.8 and at a U of 0, the constant that we're going to put into our equation is 1.13, and it's also 1.13 in all these other values. It doesn't change until we kind of get right about here. Okay, so that's why we have these lines. It's the same numbers as above. But unfortunately, what are the chances that our values are going to be exactly 0.6 or 0.8 of the ratio R over B versus a value of U? So that means we're going to have to do, again, 3 interpolations, right? Just like we did in the Theiss method, where we're going to interpolate between an R over B, 2 values of R over B, get a result, interpolate between 2 values of U, get a result, and then interpolate between those values. So it's a triple interpolation. Again, we'll do the first one together just so you kind of get the gist of it, not to leave you hanging out to dry. I'm just going to clean this up. Okay. So I'm just putting here requires interpolation for accuracy. I mean, if you don't interpolate and you just eyeball, you're going to get a rough value, but garbage in, garbage out, right? You want to do a little bit better job than just garbage in, garbage out. So let's look at a practice problem and see what we would be challenged with. So again, this practice problem is just like assignment 10. So just like lab 10. So again, if you do this one with me, you'll be set up for lab 10. And again, if you want to sketch it out, you know, if you're more of a visual learner, again, go back to page 70 and put all these parameters back into the picture. And then you could kind of hopefully force those images into your head a little bit better. Confined aquifer is overlain by an aquitard and an unconfined aquifer. Okay, exactly on page 70 and the previous page to that. The aquitard leaks. The following hydraulic parameters are given. Okay, so we have B. That's the thickness of the confined aquifer, right? And they're all spelled out here, which properties are for which. We are provided a hydraulic conductivity, meters per day. We are given a storativity, and we're given a transmissivity. Okay, what's going on with the aquitard? Here it's fairly thin with respect to the confined aquifer. So it's only 1.1 meters. It has a, look at the hydraulic conductivity on it, hey? Look how low it is compared to the hydraulic conductivity of the semi-confined aquifer. Quite a difference. And also a difference in the storativity as well. And let's look at the information that we have for the unconfined aquifer. Fairly thick, and look at that crazy permeability that we have, 35 meters per day with respect to the confined aquifer, right? So again, remember, that's going to be our source bed, another term for that, source bed. Okay, and this is the guy that's leaking. So what else do we need to know? You have to have a pumping rate, and it has to be a consistent pumping rate. So we are given here 28 cubes per day. So we'll call that Q, and it has to be constant. So again, make sure that you have a pump that can handle that, right? A constant rate. So the well is pumped at a rate of 25 meters cubed per day. It's a lot of water, okay? And what is the drawdown at a distance? So we're looking at a drawdown. So what is S? Little s, right? Not big S, at a distance of 25 meters away after 1 day. So our R value is 25 meters, and there is our time function after 1 day of pumping. But remember, before we get going on the interpolation and all the additional work, in order to determine what drawdown is, and remember our formula for drawdown goes back to right here. This is how we calculate drawdown. Okay. Well, before we go ahead and do that, we have to test. We have to test against the first case, looking at our data, and do we pass or not? And then we have to do a second test on assumption 7. So we're doing a test on assumptions 4 with a set of equations listed number 1, and against assumption 7 against the second set of equations. So let's go ahead and do that. And again, it's simply just putting in data that we've already been provided. Okay, so let's do our first assumption, our first test. And we look at our data. Sorry, let me just go back. Let's see what data that we have. Oh, that's the second test. We have time, we have that, we have that. Oh, we don't have the, we have the storativity of that, we have that, we have B, do we have B, we have K. Okay, we have that versus time. We could use this function. We have all the data for that. Do we have B double prime? We have K double prime. We have B. I'm just going to use this one. This one seems easier because that way I don't have to do any division. It doesn't matter which one you use. You just kind of pick one that you want to use. Okay. So again, you have options, which are always good. So I'm going to run my first test. And I will say, okay, this will be valid. This method will be valid if B double prime, K double prime is greater than 100 BK. So again, if you want to see the origin of these tests, you're going to have to go to the American Geophysical Union paper from the 50s, and the mathematical proofs are in there. They are not in Feder, nor they are in the course pack, but again, we're just going to take it as face value because that's the result of his analysis. So we go ahead and we look at, okay, well, this is easy to do now because what is B prime? B double prime, it was given to us as 25 meters, right? That's going to be the thickness of the unconfined aquifer. K double prime was given to us as well as 35 meters per day. Now, is that greater than 100? B, small b is 5.2 meters. Ooh, I hope it is. It's already a big number. Multiplied by K, the permeability of the confined aquifer, and that's 0.73 meters per day. So basically do math on both sides. 25 times 35 is going to be 875 meters squared per day, right? And is that greater than 100 times 5.2 times 0.73? And my calculator says it's 379.6 meters squared per day. So, boom, we have passed our first check. We can continue with the Hantush-Jacob method so far. Check number 1 is good. That means the assumptions that we made in step 4, and let me gently go back. Let me scroll up here to step 4. That specified the water table in the source bed does not fall when the semi-confined aquifer is pumped. Number 4 is proving that. Essentially, it's proving that we have infinite recharge. But now let's test number 7. If the aquitard is incompressible, no water is released from storage in the aquitard when the aquifer is pumped. And that's going to be choosing one of these sets of equations. I'm just kind of generally looking at it, and I'm going to go for the easier set again because I kind of want to do less work than more. Looks like that time function with respect to B prime, S prime, and K prime is a little easier to calculate than the square root of that other side. So I'm going to take the data for this one right here. And I know that I have time, and I already know that I have all of the data required for the aquitard. So I should be able to go for that. So as long as my supply time is greater than that function, I'm going to be good to go as well. So let's try assumption number 2, or test number 2. So again, test number 2 is if t or time is greater than 0.0366, B, sorry, I have to look back. B prime, S prime divided by K prime. Okay, so let's go see if that is the state. The T was 1 day. Okay, so let's say is 1 day greater than 0.0366. My B prime was 1.1 meter. My S prime has no units. 6.1 times 10 to negative 4, 3. You could just leave it as 0.00061. I'm just kind of running out of room here. divide that by my K prime, which is, where's my K prime? It's right here, 5.5 times 10 to negative 5 meters per day. And you could see here that we're going to be left with just a day function as our meters cancel out. So I'm just going to put that into my calculator. Did I miss a 0 there? No. Okay, 0.366. So hopefully you're working this out with me to make sure that I'm not making a mistake. Okay, and I get 1 day is greater than 0.44 days, which we know is true, right? 1 day is greater than 0.4 of a day, and we're good to go. Okay, so now we prove the efficacy of this method. Assumptions 4 and assumption 7 are valid according to these analytical equations. Remember, you can use whichever formulas you like. You have a choice there, but again, you have to go ahead and check that they are passed. And now we go ahead and look at the data table, and we get to work on the actual problem. Okay, so a little bit of a lead time work. I'm just going to have to add a page here because I've quite easily ran out. So test 1 is good. Test 2 is good. Now, what the heck was the issue? What were we going to look at first? We ultimately have to find drawdown. Remember, we're looking at S equals Q over 4 pi T times our well function. And it has this table format that we have to be able to manipulate. Okay, so we need to find a couple things. We need to calculate U, and I already gave you a formula for U. And from the table, we need to determine what R over B is. And once we get that, we could use both of these values together to get our leaking well function. And then quite simply, we just multiply that by Q, divide by 4 pi T. You're already given a transmissivity of 3.8 meters squared per day, and we're going to get our drawdown. Okay, so first things first, let's do our U calculation. And if we scroll back ever so gently, we see that U is going to be R squared S, so the radial distance squared times storativity divided by 4 T transmissivity times little t. We have all that information. Okay, so remember what that formula is. I'm just going to go ahead and copy it down. A little later right here, U is going to be equal to R squared S divided by 4 T T. Be careful that we're in similar units. We're already working in days, so we'll just leave it in days. So that's 25. I'm just going to put, is it 25 meters? Yeah, 25 meters. 25 meters. Okay, 25 meters squared. A storativity of S was 0.0035. Remember, that's a storativity of the leaking aquifer divided by 4 times the transmissivity of that aquifer was 3.8 meters squared per day. And we were running our test for 1 day. So I'm just going to put that in there. And that should be working out to what, 25 squared. I'm just going to round it off to 3 decimal places. I get 0.144. Of course, we're going to lose our meters squared, our units. We're going to lose that. We're going to lose that. Our day an numerator with respect to the denominator, they're going to cancel out, and we're just going to left with a u of a 0.144. So that's one piece of information that we need. Let's carry on. Our R over B. So if we go back to U, we have the data for this column, and we had a 0.144. So somewhere our data is going to be here, 0.144, right? And we know that we're going to be in this band here. Let me change the highlighter here. We know we're going to be in this band somewhere of data for our ultimate well function. Okay. But where are we going to be with respect to R over B? Well, we have to calculate that. So if you'll remember, I modified the equation ever so slightly by adding our radial distance. Okay, I just basically pushed everything to the denominator. So our R over B function is going to be equals R divided by the square root of TB prime over K. Again, as applied to us by Hantush, I did not make this up. And we don't have to worry about the proofs. That's not what we have to worry about. So I'm just going to rewrite that down for myself. R, before I forget, R over B is equal to R over the square root of TB prime over K. Is it K prime or K? I have to look again for myself. I'm sorry, I have to scroll back. It's K prime. K prime. Hydraulic conductivity of the aquitard. Okay, so we have all that information as well, right? So we had, I'm not gonna put in units here because I don't want to run out of room. We have 25 meters divided by the square root of the transmissivity. We already said that was 3.8. Our B prime of that thin bed was 1.1 meters. Divide that by K prime, which had that very low hydraulic conductivity of the aquitard, 5.5 times 10 to negative 5. And let's work out what that is. Give me a second. I seem to have lost where my square root. Oh, there it is. Okay. Okay, and I got an answer of, and hopefully you did too, 0.0907 for an R over B. Okay, so I have all the data that I need in order to do my interpolation. So if I go back, remembering what this value was, 0.0907 for the ratio of R over B, that's going to put me right about somewhere in here, right? 0.0907 between 0.08 and 0.01. So it looks like I'm going to be interpolating these values. Okay. So again, I'm forced to do a triple interpolation, right? I have to interpolate between these points, and then a third point in between to get the value that I could use for my well function, which is right here, my well function. Okay. So we're getting there. We're almost there. So I'm going to I'm not going to do the interpolation for you, but I'm just going to do the setup for the interpolation, just so you can look back on your notes. So by now you should know how to do an interpolation, a triple interpolation like this, but I'm just going to set it up for you. And then we'll just kind of continue going on with the results of the triple interpolation. I might as well start just putting the interpolation formula on again for you all in case you don't have it handy. I do, I have it written in my notes, so I'll just go ahead. Okay, so I'm not going to do the interpolation for you, as I said. By now, you have to be able to do those interpolations, and that's something that you would have done in first year too, or in high school. So what I got, and I'm not going to go ahead and do a plug-in and delta formulas, but when I triple interpolated, I got a value of 1.55. And ask yourself, does that make sense? So as I go back and I kind of look at the data here, I basically interpolated between 1.81 and 1.22, and then 1.8 to 1.22 again, and then between those results to get a value of 1.5 because my U function was 0.144, so I'm kind of sitting right in the middle. Again, I could have probably estimated, I knew it was going to be around 1.6, but you don't know until you know, right? So you have to go through that workflow. And then once you have that result, boom, you're almost done. You already know that your drawdown is going to be equal to your constant pumping rate divided by your 4 pi transmissivity times your well function, but which you've already calculated that. So again, if I want to just put values to that, we were pumping at 28 meters cubed per day, divided by 4 pi. Your transmissivity again was 3.6 meters squared per day. And now this replaces all this, right? All your hard work from your interpolation is basically comes down to this, 1.55. And you're going to see that we're going to do the same thing with the Walton method, and we're going to be curve matching. And the cool thing about curve matching is with curve matching, we're going to reduce this to 1, so we won't have to do all that interpolation work. But then again, when you're curve matching, everyone's going to curve match a different thing, and maybe the accuracy won't be there as much as possible. So long story short, under those conditions, if you're 25 meters away, you work out that you're going to have a drawdown of just over 0.9 meters from your well with those conditions and those leaking conditions. But again, remember the workflow. Before we got to that point, we had to test the efficacy of the Hantush method. Does it pass the initial assumptions? Choosing between those 4 equations, but actually choosing between the first 2 equations in the first step and the other 2 equations in the second step, and then calculating U, calculating R over B, so we could go back and find where we need to be within our data table, doing that triple interpolation in order to get our well function and put that, nesting that back into the formula. So that's kind of how it goes. Just have to honor the process. I don't think it's difficult. It's just kind of time consuming. And as a result, and let me just talk about the lab, and then I'll let you work on the lab. Or I'm going to take a 10-minute break myself, but I'll let you kind of look at the lab and see how you're going to go about it. I would heavily suggest you do this in Excel because it's a lot of calculations. Assignment 10. Answer the following questions using the Hantush-Jacob analytical method. Do not round your answers until the final drawdown calculations, and ensure you are interpolating when using the well function table. Again, if you round too early or if you don't interpolate but eyeball, your values are going to be wrong. And there should be absolutely no reason why we have different values as long as we do that. And when I'm checking your work, because it's not a graphical method, it's just an analytical method. Compile your answers for each question into a table. Given the repetitive nature of the calculations, you may choose to use Excel. I highly encourage you to use Excel. So, but all the problems are exactly the same. The community is installing a new well in a semi-confined aquifer with a transmissivity given and a storativity given. Okay, so that's going to be your T and your S, big S. The aquifer is overlain by a B prime, 13.7, right? Foot, and again, we're working in imperial units. So that's going to be your B prime with a vertical hydraulic conductivity of this. So that's going to be your K prime. The planned pumping rate is this. That's going to be your Q. So everything's kind of coming together, right? You're starting to get your variables as you're going variable shopping. You can identify them pretty easily. There are several nearby wells, which means we're going to have a whole bunch of R's, right? To think about. Installed in the same aquifer, and a project manager, your PM needs to know if the new well will cause significant interference with these wells. So basically you're testing for a drawdown, right? If I go ahead and if I pump this well at 325 gallons per minute, what kind of drawdown am I going to cause with these other nearby wells? So compute the theoretical drawdown caused by these new wells after 30 days. So there's my T function. And look, here's a whole bunch of R's. Continuous pumping at various R's. That's why we say it's repetitive, because we want to check it at all these radial distances, all the ways up to over, well, it's almost 2 miles away, right? So again, it's like you're doing one of the problems that we just did, but you're doing it 1, 2, 3, 4, 5, 6, 7, 8 times, but it's only for question number 1. And then look at your data, right? Does your data make sense? Tell your project manager what she wants to know. And then just changing around the variables a little bit. A well that's screened in a semi-confined aquifer is pumped for 30 days. Aquifer is overlain by 8 feet of an aquitard having hydraulic conductivity. If the aquifer transmittivity is T and the storativity is this, what is drawdown again at other distances? It's basically the same problem, kind of, with different variables and whatnot. And then with number 3, with reference to the well and aquifer system and problem number 1, compute the drawdown at a distance of 100 feet with different times, right? So basically you're just looking for different variables with either minutes and days, just kind of rearranging your spreadsheet or your calculations to calculate based on time instead of radial distance.